Okay, hello Precalc C. Last week we did a lot of counting and we went over some problems from the counting problems packet last week, but we didn't go over some of them. So let's go over the ones we didn't go over now. Here we go. Number 8. I'm just going to read these aloud. Number 8 says, there are 5 finalists for the U.S. bid for the 2016 Olympics. And those, so every country has their own sort of nominating process in which they narrow down to a single city, and then they submit that to the International Olympic Committee, and then from that they select a city. So the United States had to pick which city they were going to put forward as their nomination. And the choices were Chicago, Houston, Philadelphia, Los Angeles, and San Francisco. So 1, 2, 3, 4, 5 different cities. So there was some kind of committee, and I think this is actually how they do it. A committee ranks their top 3 choices. And so with those 5 cities, we have to pick, and the first place votes are worth 5 points, second place votes are worth 3 points, and third place votes are worth 1 point. How many different ballots are possible? Okay, so that means that basically when we say how many different ballots are possible, what we mean is how many different ways can one person on the committee fill out their ballot? Well, we have these 5 cities. Let's just call the 5 cities A, B, C, D, E, but they're really like, Chicago, whatever, Houston, whatever. And from these 5 cities, I need to rank one of them 1, one of them 2, and one of them 3. The point values are irrelevant for this problem, but all that does matter is that you do get different numbers of points if you rank first, second, or third. So it sort of does matter, and we do care on a particular ballot which city is ranked first, second, and third. Okay, well, I think this is not hard. This just basically just boils down to, one way of looking at it is you have 5 choices for who to pick to rank first, and you have 4 choices for who to pick to be ranked second, and then you have 3 choices for who to pick to be ranked third. So there are 5 times 4 times 3 choices, and therefore the answer is 60. You could also think of it as 5p3. You are permuting 3 of the 5 cities. Okay, that was number 8. Number 9, maybe I'll just kind of squeeze number 9 in right here. Number 9 says, the starting lineup for a baseball team consists of a pitcher, a catcher, a first baseman, second baseman, third baseman, shortstop, and 3 outfielders. We're just categorizing all the outfielders as being sort of indistinguishable. And, okay, who's on this baseball team? A bunch of each. 8 pitchers, 3 catchers, 2 first basemen, 2 second basemen, 2 third basemen, 2 shortstops, and 5 outfielders. How many starting lineups are possible? Okay, well, we're going to have 1 pitcher in the starting lineup, and there are 8 pitchers to choose from. Then we have to pick 1 catcher. How many catchers do we have? 3. So there are 3 choices for which catcher, and the multiplicative principle is in play here. For every choice of which pitcher, there are 3 choices of which catcher. So there are 24 sort of pitcher-catcher combinations. Next, what are we doing? 8, 3, 2 first basemen, and so we need to pick 1 of those 2 first basemen. There are 2 second basemen, so I multiply by 2 again. There are 2 third basemen, so I multiply by 2 again. 2 shortstops, so I multiply by 2 again. This is a silly problem. And finally, from among the 5 outfielders, I must pick 3, and there are 5 choose 3 ways of picking 3 outfielders from among the 5 outfielders. Okay, this is a little bit of a dumb problem because it sort of does matter who goes into right, left, or center field. But anyway, that was kind of the idea of that. But this is a stupid problem. Number 10. This one is, I think, the hardest problem in the entire packet. And here's what it says. 5 couples go out to dinner and sit at a rectangular table with 5 chairs on each of the longer sides and no chairs on each of the shorter sides. Each couple must sit either next to each other or across from each other. How many seating arrangements are possible? Men. 5 couples walk into a restaurant, and these 10 people are now going to sit down in couple formation, though even the couple formation is open because the couples can sit next to each other or across from each other. And the question is, how many ways can this happen? Alright, I think this is quite a hard problem, and once again, I think the solution to it requires that you emotionally kind of engage in the story. So you need to make yourself part of the story, and you need to think, okay, how would I do this if I had total power? So you need to kind of say, alright, here I am, I'm at the restaurant, I'm setting up the table, I'm deciding where the couples sit. The couples are waiting outside, I'm about to let them in my restaurant, and I'm going to sort of tell them where to sit. How many different ways can we do this? Alright, this is really like a kind of a two-part problem, because if couples can sit next to each other or across from each other, then before we even talk about which couple sits kind of in which position, we should talk about the number of different valid positions there are. And I think this is kind of the hardest part of the problem. To read exactly what it says again, there are 5 chairs on each of the longer sides and no chairs on each of the shorter sides. Each couple must sit either next to each other or across from each other. So let's catalog all of the valid positions that couples can sit in at the restaurant. Alright, well, here is my table. One option is that the couples all sit across from each other. And so I'm going to indicate that like this. So each one of these is a single person, and perhaps we can even connect them or something with a line to indicate that these are the couples. That's one way. And you could even take it a little bit further and imagine that you're sort of setting the table up for some kind of Valentine's Day kind of thing, and you are going to put a place setting in such a way that a couple has to kind of sit. If you set the table that way, the couple needs to kind of sit accordingly. All right, well that's one option, but it's also possible for couples to sit next to each other. Well, what's one possibility is that the couples, that only one pair of couples sits next to each other on any given side of the table. In other words, imagine that these two just decide to sit next to each other. And the remaining 3 on that side of the table are arranged in the other kind of fashion. So that's a couple, and that's a couple, but then that's a kind of a couple blob over there. Well, based on the way the problem was explained, couples need to sit either next to each other or across from each other. And so the 2 people sitting opposite this couple that's sitting next to each other must also sit next to each other. Okay, so this is a valid table arrangement as well. And then, of course, there is the option for the couple blob to be not on the left, but sort of in one. So in other words, we have kind of this type situation. And maybe this problem is now kind of coming into focus a little bit. Couple, couple, couple. That's also a possible valid sitting position. And okay, I think there are, I'll just draw them all because why not? But I think there are 2 more, right? Owing to the fact that the couple blob, assuming that there's just one, could instead be sort of 2 in. So 1, 2, 3, 4, 5. Or all the way on the other side. So 2, yeah. So 1, 2, 3, and then the couple blob. Okay, so I claim that this completely describes the possible ways to set the table if there is one couple sitting side by side on each side of the table. But it's also possible that there could be more than one pair of couples that chooses to sit side by side. And so the other option is something like this. So that's and like that, or something like that. Okay, and I think you can already see now that what are the other possible arrangements that meet this same specification? Well, the couple which is sitting opposite each other basically could be all the way on the right, in the middle, or all the way on the left. So there are 3 more of these. So we get a little bit of this type action. And finally, this kind of thing. Okay, so great. And just finishing off the picture, something like that. Okay, and I think that there's just no other possibility because there are only 5 seats on the side of the table, so we can't fit 3 couples, of course. We can only fit 1 couple or 2 couples. So either there are going to be no couples sitting side by side, 1 couple sitting side by side, or 2 couples sitting side by side per side of the table. So after this kind of exhaustive analysis, I could have drawn fewer pictures if I was being a little bit smarter, but I might as well just draw them all. I claim that there are 8 distinct ways to set up the table. Okay, and so if you are imagining yourself in the role of the person who's setting up the tables, then there are 8 ways to do it, and that's even before the couples arrive. So there are 8 possible table arrangements, and for each of those table arrangements, there are of course many different ways for the couples then to walk in and sit down. And in fact, how many ways are there for them to do this? Well, I think this first case maybe is simplest, right? If there are 5 couples, then first of all, the couples need to decide which couple is going to sit where. So there are 5 choices for which couple sits here, 4 choices for which couple sits here, etc. So I think one way of doing this is saying, okay, well, there are 5 factorial ways for the 5 couples to permute themselves. In other words, there are 5 factorial ways for the 5 couples to decide which couple sits in which couple spot. But even having decided which couple sits in which couple spot, each member of the couple is free to sit in either of the 2 spots. And so now, couple 1 needs to make a decision, and they have 2 options, right? Here or here, amongst the 2 people, whether they sit in each of those 2 spots. And the second couple also has 2 choices, whether the 2 people want to sit, which of the 2 options they want to follow for who sits where. And so, okay, so for each of the 5 couples, they have 2 choices about which member of the couple sits in which spot. And so the final answer here is this is 8 times 5 factorial times 2 to the 5th. And I get that this is 30,000 times 30,720. Okay, so I thought that was a pretty hard problem. There's another sort of way of thinking about this that's a little bit different than what I just did. And that is to go like this. Let's see. Well, here, maybe I'll just do it kind of here, right? So how many choices are there for who sits there? Well, there are 10 choices for who sits there. But having chosen, maybe I'll just erase this. Having chosen, and I should say that this entire analysis of 5 factorial times 2 to the 5th applies to each of the other 7 table arrangements as well, right? All of them sort of have the property that there are 5 kind of slots for couples, and those slots are all different. So for each of these 8 table arrangements, there are 5 factorial ways for the couples to arrange themselves, and then within each couple there are 2 choices. So one different kind of approach, maybe that's a little simpler somehow, is to say, okay, there are 10 choices for maybe the first person who walks in has a choice of whichever seat they want to sit in. But once this person has sat there, then there's only 1 choice for who sits there, because it has to be the other member of that couple. And then, how many choices are there for who gets to sit here? Well, there are 8 choices for who sits in that spot. But then, once again, only 1 choice then for who sits here. Then there are 6 choices, because there are 6 people left, for who you're going to pick to sit in that seat. But then there's only 1 choice for who sits opposite them. 4 choices, because there are 4 people remaining, for who sits in that seat. And there are 2 choices for who sits in that seat. And so the answer is 10 times 8 times 6 times 4 times 2. But of course, if you factor 2 out of all 5 of these numbers, then that just is 5 factorial times 2 to the 5th. So that's a different way of doing it. Okay, you can do something really fascinating with this problem, which is if you want, you can abstract away and prove a sort of more general fact, which is, this was the case for 5, and notice how we counted kind of by brute force the number of table arrangements that were possible. We got 8. And you might ask yourself, okay, what if there were fewer? What if there were only like 4 couples per side? Then how many arrangements are there? Well, I claim that there's 5. So there's this one, cha-cha. There's this one where we got Jean. And then, okay, this is getting kind of silly. I want to move on, but then you could also have something like that, cha-cha-cha, and two more. There is the one where the couple blob is all the way on the left, and finally, there's the one where there are just two couple blobs. Okay, so that's 5. In fact, if you examine this more carefully, you will see that the number of tables is in fact following the Fibonacci sequence. And that is pretty crazy. I think it's following the Fibonacci sequence, not counting 1. So it's following a Fibonacci-like sequence. There's one way to sit a couple if there's only two people. That's one answer. And then if there are going to be two couples, then there are 2 ways to do it. There's that way and there's that way. 3 I'm not going to do, but the answer is 3. If there are 4, then the answer is 5. If there are 5 couples, then the answer is there are 8 ways. And so if you want a challenge, you can try to prove in general this pattern for this same exact problem, but now with a kind of arbitrary number of couples, say n couples. And the answer is it's the n plus first Fibonacci number. So okay, try that proof. Great. All right, let's do the rest of this. 12, 13, and 14. Mm-hmm. Okay, 12 says how many ways can 10 persons form 2 groups of 4 and 6 persons? Okay, that's a very boringly phrased problem, but we have 10 people and we need to split them up into 2 groups, a group of 4 and a group of 6. Okay, but that's just like choosing 4 people, because by choosing 4 people out of the 10, then there are the 6 left over that you haven't chosen. And so any way of choosing 4 from amongst 10 is a way of splitting that group of size 10 into a group of size 4 and a group of size 10. And so the answer is the number of ways of splitting these 10 people into 2 groups of size 4 and 6 is just the number of ways of choosing 4 people. That is 10 choose 4. Let's just do this just for fun. So it's 10 factorial over 6 factorial, 4 factorial. So it's 10 times 9 times 8 times 7. Over 4 factorial, so 4 times 3 times 2, and I think we get 321, 210. Yeah. Okay, 13 and 14 are both kind of interesting and maybe a little bit tricky. 13 says, in how many ways can 10 people be lined up so that a certain pair of them are always next to each other? Okay, so we have 10 people. So imagine this is a 5th grade field trip, and we are going to get in a line for some kind of activity, and there are 2 people that are best friends, and they're such good friends that they demand that they are going to be next to each other in line. So if you're the teacher, how many ways can you arrange these 10 people in a line, but making sure that these 2 people are always together, because if they're not, they'll cry or something. Okay, well the idea is that you just can imagine yourself in the situation and have these 10 people. But do I really have 10 people? I really kind of don't, because these 2 best friends are holding hands, and if you separate them, they will cry. And so if you separate them and they cry, then don't think of them as 2 different people. Think of them as just one person, one sort of blob of best friends that must be next to each other. So then you say, okay, well then there are really just 9 factorial ways to arrange these 9 groups of people. 8 of those groups are just consisting of individual people, and one of those groups is this blob of best friends that are holding hands. And so there are 9 factorial ways to arrange them. Having then decided in what order all these people are all going to be. Now there's one more choice to make, which is because in fact everyone is lining up single file. So for every one of the 9 factorial ways there are to line up these 10 people, I still have 2 choices, and the 2 choices are for the 2 best friends that are holding hands. One of them needs to be first and one of them needs to be second, amongst themselves. So answer 9 factorial times 2. Okay, that was part A. Part B illustrates kind of an important idea. What if now, so that was the morning, and then these best friends forever, what did I say, 5th grade? They get in a big fight, and now they are sworn enemies. So now you gotta keep up with the latest gossip a 5th grade teacher does. And so now we're lining up to get on the bus to go back home. And now we better not put these people next to each other, because if these 2 people are next to each other, they're gonna cry. And so we now need to count all the possible ways to line up the students so that these 2 are not next to each other. Alright, well, if I gave you this problem in a vacuum, you might be thinking, man, how am I going to do this? This sounds so hard. How do I count the ways that something doesn't happen? Well, the very fact, and anytime you find yourself in a counting problem where someone's asking for the ways to sort of not happen, you should take this as a tip that we should just consider all the ways it can happen, and then subtract out the ways then subtract from the total number of ways. In other words, the solution to this problem, this is called complementary counting, is you just take all the possible ways of arranging the 10 people, ignoring the fact that we have these 2 best friends who are now enemies. There are 10 factorial total ways to do this. And now all you have to do is subtract out the ways in which they're sitting next to each other, and then you're done. Right? So take all the number of ways of arranging the 10 people, subtract out the number of ways, which we counted in part A, for them to be next to each other, and then you get the number of ways in which they're not next to each other. Okay, cool. 14 is a similar kind of thing. 6 boys and 6 girls are to be lined up in such a way that boys and girls alternate. How many different ways can this be done if a certain boy and a certain girl must be together? Okay, so this is a kind of follow-up on the previous problem. We have 6 boys and 6 girls. They're going to be arranged in kind of boy-girl order, alternating. And there is a particular boy and girl who are best friends, and they want to be next to each other. So, okay, well, if they want to be next to each other, then they're sort of already one kind of boy-girl pair or something like that. So you might try a similar kind of analysis. You might think, oh, isn't it just kind of 6 factorial, which is the number of ways of arranging them, and then actually I don't even know what you would do exactly. So because it's not really 6 factorial. It's like you want to split them all up into couples. Okay, the problem is that if you think of this whole thing, I'll explain why this is hard in a minute. And then here we have, okay, so we have this sort of 6 slots here, right? And, okay, boys and girls have to alternate. So the first person in the line, let's imagine the line is, facing this way. The first person in the line is going to be either a boy or a girl, and then the next one will be, one or the other, blah, blah, blah. So the problem is that this particular boy and girl that must be next to each other, you don't know for sure whether they fall into one of these slots. They could also end up falling across kind of a barrier that you've mentally kind of constructed here. So this problem is actually a little bit more difficult than it seems at first, because I'm not sure, I can't really split these 12 students up into 6 slots and then be sure that the particular boy and girl that I'm talking about that must be next to each other are necessarily going to be in one of those slots. It's not that easy. Okay, and so in fact, what we need to do is we need to sort of count consecutive positions. So you have to sort of look at this whole arrangement and say, okay, what are all the possible consecutive positions? So we're going to place basically, once again, put yourself at the center of the action. There is this particular boy and girl, they're best friends. Where are we going to put them? Once we decide where to put them, then we'll fill in everybody else around them. Well, where can we put them? There aren't just 6 options for where to put those boy and girl best friends. There are more than 6 options because, and now I'll maybe kind of draw this in or something. You know, we have this is a spot to put them, this is a spot to put them, this is a spot, this is a spot, this is a spot, and this is a spot. But then there's also kind of like this spot, this spot, this spot, this spot, and this spot. Okay, so if you count that all out, you realize that there are actually 11 different positions in which you can place a pair of people if you have 12 slots to put them in. And so there are 11 choices for where we put that boy and girl best friend. Having decided where to put the boy and girl best friend, once we drop them into a particular slot, say here. Say it turns out that we end up putting them here. So I'll just call this you know, boy 1 and girl 1. They're like my special boy and girl that want to be next to each other. Well, if boys and girls must alternate, then once I drop a boy and girl pair into my arrangement, then the order of boys and girls now is fixed. Okay, and so you have to think of this as kind of 3 separate options. Step 1, there are 11 choices as to where I place this boy and girl best friend. Then, having decided that they fall into this spot, I have 2 choices about whether the boy goes first or the girl goes first, amongst those 2 that are best friends. Having decided where the boy and girl go relative to each other, that now fixes every remaining spot as either a boy spot or a girl spot. And so, okay, the colors are getting a little crazy here, but if that's a boy, then that means that this is also going to be a boy goes here, and 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 a boy goes here. And so now I have 5 remaining boy spots, and I have 5 remaining boys. So I multiply by 5 factorial because there are 5 factorial ways to place the boys into the 5 boy spots. And that leaves 5 girl spots, and so there are 5 factorial ways to place the 5 girls into the 5 girl spots. And so, yeah, this is just what we get, right? For every one of those 11 spots, for every one of those 11 places where we can place these particular 2 best friends, then there are 2 choices for how they align themselves with respect to each other, and that then fixes every remaining spot in the line as either a boy spot or a girl spot. 5 factorial boy spots, so 5 factorial, sorry, 5 boy spots, so 5 factorial ways to fill in the boys, and for each one of those ways, there are 5 factorial ways to fill in the girls. Okay, oh, no, we're not done. That's part A, and then part B, well, this is the same trick again, right? Part B says, what about if they must not be together? So now there's a particular boy and girl that hate each other, and if you put them next to each other, there will be crying and screaming and fights. Well, this problem in general is hard, but we can solve it by using complementary counting. In other words, we'll just take the set of all possible valid ways to fill in 12 spots with 6 boys and 6 girls in alternating fashion, and then subtract out the answer that we got in part A. Okay, so if there are no special people who hate each other or like each other, then I claim there are the following number of ways to fill students in into this 12-person line. Well, there are 2 ways, because first I have to choose whether boys go first or girls go first. Then for each one of those ways, now there are 6 factorial ways to fill in the 6 girls, and for each of those there are 6 factorial ways to fill in the 6 boys. So this is the answer to the general problem of how many ways there are to arrange 6 boys and 6 girls in boy-girl order. And if I subtract out the number of arrangements in which this pair of boy-girl best friends are next to each other, then I've just counted the number of ways in which they're not next to each other. Okay, well that was pretty good. See ya.